Let's say you're given these two equations, y equals kx plus 2 minus k, and y equals 9 over k times x minus 1. These are actually equations for two straight lines, but there is an unknown value of k inside each of them. This means we don't actually know how these two lines behave. They could be parallel to each other, they could be coincident, overlapping each other, or they could be crossing each other, intersecting at one point. Depending on what the value of k is, you could get any of these three situations. So using two examples to compare the slopes and the y-intercepts together, I will show you how you can find a suitable k value for each of the three scenarios, and I'll be putting all of that into a neat little table so that it's easier for you guys to understand everything. The first and most important thing you want to do here is note which bit is the slope and the y-intercept for each equation. So for the first equation, the slope is k, which I will call m1, and the y-intercept is 2 minus k, which I will call c1. As for the second equation, 9 over k is the slope, and negative 1 is the y-intercept. Depending on what you put for the value of k, the lines could end up being parallel, coincident, or intersecting with each other. The easiest way to go about doing this is to find out what values of k will cause the gradients to match, and what values of k would cause the y-intercepts to match. Starting with m1 equal to m2, substitute the slopes in and we will see that k equals to 9 over k. Rearrange that and we will see that k equals to negative 3 or 3. So what does this mean? It means that when you substitute any one of these values into both equations, their slopes will be exactly the same. And so by using only one of these two values, your lines will either be parallel or coincident. If you pick anything else, your lines will simply cross each other. But we need a little bit more information. So let's find out what the value of k will be when the y-intercepts match. We can see that when c1 equals to c2, 2 minus k equals to negative 1, and that simplifies down to k equaling to 3. So at this point, it can be pretty difficult to try and decipher what's going on, and this is why I came up with a table format to try and organize this information. We can see that when k is negative 3, m1 equals m2. At the same time, that doesn't exist for c1 and c2, so we will say it does not equal for that column. Based on this combination of information, we would say that the lines are parallel. But when k is 3, m1 equals to m2, and c1 also equals to c2. Since everything equals here, it must be the coincident case. As for everything else that you can use for the value of k, m1 will not equal to m2 because there is no other solution for that, and c1 will not equal to c2 for the same reason. And this would be the combination for two lines that cross each other over one point. If you guys are wondering how I used the equals and not equals sign to determine the type of interaction we're dealing with, please have a look at my previous video. It explains everything about how these lines interact with each other. This video is purely just about the algebra and working out how to establish different scenarios or interaction types between two lines. Alright, so let's move on to the second example, which is a little more difficult and also has a special case involved. Alright, so with these two new line equations, again, just take note of which bit is the slope and which is the y-intercept, and begin by first finding out when the k values will cause the slopes to equate to each other. So we have k plus 3 equals to 6 over 4 minus k. When you do the algebra for this, you will find that it is going to be some kind of quadratic, which will yield two results. And so when the value of k is negative 2 or positive 3, the slopes will equal to each other, but not at any other time. As for the y-intercepts, equate 12 over k minus 1 with k minus 2, and after a little bit of algebra and factoring, we can see that k equals to negative 2 or positive 5. And as like in the previous example, we can see that both equations have a common answer of negative 2. That would be the coincident case. But the 3 and 5 makes this very confusing to try and work with, so we're going to set up another table to see how this all fits together. Alright, so when k is negative 2, we can see that m1 will equal to m2 and c1 will equal to c2. And since everything matches, this must mean the two lines are coincident with each other. When k is positive 3, only the slopes match. The y-intercepts don't. There is no solution there for it. And so this would be the parallel case. When k is 5, the slopes do not match, but the y-intercepts do. This is the special case. This is something that was not in the previous example. This is special because the lines will cross each other at one point, and that point happens to be the y-intercept. So these two lines intersect on the y-axis. As for everything else that you can plug into k, the slopes will not match, and neither will the y-intercepts, since there are no other solutions for those two equations. And this will be the typical case of where two lines cross each other at one point anywhere besides the y-axis. As far as writing an answer goes, you can say that to create no solutions, which is the parallel case, k will equal to +3. The coincident case would create infinitely many solutions, and this would be when k is -2. As for the case of one solution, where two lines will cross each other at only one point, you can say k is not equal to -2 or +3. In other words, you're saying that the value of k can be anything except these two numbers. Keeping in mind that when k is equal to 5, that is a special crossing case over the y-axis. Alright, so I hope you guys enjoyed this video. Let me know what you think down in the comments below. If you found this helpful, hit that like button and share it with your friends. Have you joined the channel yet? If not, hit the subscribe button down below and ring the bell so that you can get notified for when the next video comes out. Thanks so much for watching, guys. Have a good one, and I'll see you next time. Bye!